second half of the video, we're going to be looking at a couple of buff titration problems where we look at both strong acid, strong base, as well as weak acid, strong base. And then we're going to look at a Ksp problem. So we're going to start by noting that this titration here, we have a 10 milliliter sample of nitric acid and we're titrating with sodium hydroxide, and we're given the volume and concentration that it takes to reach the equivalence point. So for this problem, we want to note that it's a strong acid, which means we should use all of our strong acid concepts rather than our weak acid concepts for the problem. So you have to start by noticing that. So because it's HNO3 and sodium hydroxide, these are going to react in a 1-to-1 ratio. Because of that, when we're looking for the concentration of the nitric acid, at the equivalence point, we know that M1V1 equals M2V2. Note that this is only true because this is a 1-to-1 reaction. If it weren't, then this wouldn't be a true statement. So I can plug in my numbers now. That we have 0.100 molar for the concentration of our sodium hydroxide, and then we have a volume of 0.0115 liters for the volume. Then we don't know the concentration of our nitric acid, but we do know that the volume is 0.0100 liters. Note that if you had decided to make nitric acid M1V1 and sodium hydroxide M2V2, you'd be fine as well. Both work. So here we plug in the numbers, and we get the M2 is simply 0.115 molar. And so that's all we've got to do to get our concentration here. Now, question B. What is the pH before any base is added? So this is simply the pH of a strong acid. So we have the pH of an acid which has initial concentration of 0.115 molar. So that is going to be negative log 0.115. And so that is going to give us a pH of 0.939. That's our pH. So that'll get us through our first two questions. So you'll notice with both of these that one of the issues is it's about identifying what you have to do, because this portion of the problem wasn't too long, but you had to know, okay, I just take the negative log of the concentration of the starting acid, and then to use M1V1 equals M2V2, or some other way of calculating the molarity at the equivalence point. So now, let's look at question C. So for C, we want to know what is the pH after 5 milliliters is added. So first, because once we start adding volume, we have to start dealing with moles. This is because our concentrations change as our volumes get adjusted. So we want to start working in moles until the end of the problem. So any of the additions of acid and base are going to require figuring out how many moles we have of both the starting acid as well as the base we added, and then using a BAA table. The way I know I'm using a BAA table is because I'm adding a base to an acid or an acid to a base. So I've got to account for the fact that these volume changes are adjusting the concentrations. That's how I knew I wanted to do this. So our moles of acid, and I'm going to show the calculation this time. I'm going to assume you know how to do it when we get to the later parts of the problems, like on the second example. For this one, I'll show the full calculation. So we have 0.0100 liters. That's how much acid we have. Yeah, because we have a 10 milliliter sample. And so we know that it is, from part A, we know the concentration. So this is 0.115 moles per liter. And so we have 1.15 times 10 to the minus 3 moles of our acid. We then need to find moles base. And for that, we've added 5 milliliters. So currently we're at 0.0050 liters. And we know that for every 1 liter, it has a concentration of 0.100 moles. So we have added 5.0 times 10 to the minus 4th moles of base. So now our reaction is we start with nitric acid, and we're reacting it with the hydroxide ion. That's what we get from our base. It would also be okay if you just wrote this as H+, since it's a strong acid. That would be okay as well. Both are true, and because it's a strong acid, strong base, we're just going to have this go one direction. And we're going to have the nitrate ion, plus we've got water. So here are before, so at our start, we had 1.15 moles times 10 to the minus 3. We had approximately no hydroxide at the start. We had none of this. We didn't have any water. So in our addition, we didn't add any more nitric acid. We did add some hydroxide. We didn't add any nitrate. So then after our addition, since there's less hydroxide than there is nitric acid, all the hydroxide is going to get used up. Remember, we're not going to have both of these present at the same time since the hydroxide is a base and it reacts with the acid because we added a strong base to this. So it reacts, it neutralizes some of the acid. Specifically, it neutralizes 5.0 times 10 to the minus 4 moles of the acid. So if we subtract this from the amount of starting nitric acid, we get that we have 6.5 times 10 to the minus 4 moles remaining. We then also have 5.0 times 10 to the minus 4 moles of nitrate. Note that we don't have to worry about this number in the strong acid, strong base case because the nitrate ion isn't going to go back and form nitric acid. So we're not actually worried about this, but it's good to note to be used to it for when you do other BAA tables with weak acids where it does matter. So now we need to know what the concentration of our HNO3 is once we've added this base. And so that's going to be 6.5 times 10 to the minus 4 moles. And from that, we have 0.015 liters. And we get a concentration of 4.33 times 10 to the minus 2 molar. And for here, we get pH is equal to the negative log of this concentration. And so our pH is going to be equal to 1.36 after we have added 5 milliliters of base. So that gets us through C. Now let's look at D and E. So D is actually a very quick question. So D, pH equals 7. And you're done. This is because you have a strong acid and a strong base. That means at equivalence, pH is equal to 7. That's true for all strong acid, strong base cases. That's all you have to do. Now for E. In the E case, we again have a BAA table, as we're going to have, but this time we're going to have excess hydroxides. We have more hydroxide than we have at the equivalence point. So we need to note that our moles of base, and I'm doing this the same way we did earlier when I showed the steps in part C. If you do that same work, you're going to get 1.5 times 10 to the minus 3 moles of base are added. We then know our reaction is we're reacting nitric acid with hydroxide. Remember, you could also put this as just H+. That would be okay because you have a strong acid. Just note you can't do that if it was a weak acid. And then from there, we have NO3 minus plus water. Our before is still the same because this is just the starting point. So we get this back from when we solved it earlier. The difference now is our addition is different. We're still not adding any nitric acid, but we're adding more hydroxide. What's important here is to note you have more hydroxide than you do nitric acid. This means that after the addition, all the nitric acid is going to be used up. We're not going to have any left. And so if we use up all the nitric acid, we can subtract that from the amount of hydroxide to see how much hydroxide we have left over. And we'll have 3.5 times 10 to the minus 4 moles. That's because we took 1.5 times 10 to the minus 3 and subtracted 1.15 times 10 to the minus 3. Then you'll also have this much nitrate ion left, but note that that doesn't matter in this particular problem. We then know that we've got excess hydroxide. So our OH minus concentration is equal to our 3.5 times 10 to the minus 4 moles over our new volume, which is now 25 milliliters or 0.250 liters. That's because you had 10 milliliters and you added 15. And from that, we get that our concentration is 1.40 times 10 to the minus 2 molar. We can then say that the POH is equal to the negative log of 1.40 times 10 to the minus 2. So POH equals 1.85, and pH is going to be equal to 14 minus 1.85. So our pH of our solution is 12.15, and this makes sense. As we are now in the excess base region, we should get a pH that is significantly above 7. If we got something below 7, we probably did something wrong there. So that'll get us through our acid strong base titration. Next, we're going to look at a weak acid, strong base titration. Note that in general, these problems, as long as the last one may have seen, these tend to take a little longer once you have a weak acid because there's more steps you have to do for some of these problems. But for part A, it actually ends up being the same. My pointer disappeared. There we go. So for part A, we've got a 1-to-1 reaction. Hydrofluoric acids react with sodium hydroxide. We've got a monoprotic acid, and our base only has 1 hydroxide. So we don't have to worry about different number of mole ratios. That means that M1V1 is going to equal M2V2. Remember, this statement is only true when the number of moles are equal. So if we plug our values in, we get 0.100 molar of our sodium hydroxide, And the volume of that was 0.0135 liters in the case for this problem. And then we have M2 times, again, our volume. We didn't have a 10 milliliter sample, so 0.0100 liters. So here, we're going to get the M2 is equal to 0.135 molar. Now, that's all we have to worry about for part A. Now, what I'm going to do is, when we get to part B, I'm actually going to go ahead and clear the slide because it takes a little bit of work, just in case I don't have room. So, for B, we now have that we want to know the pH for any bases added. So in this case, we now have a weak acid. So we have to go back and do the same type of thing you would do for the concentration of H3O plus for a weak acid. That means we need to write out our reaction, which is hydrofluoric acid plus water is going to be in equilibrium with, remember the arrow goes both ways this time, F minus plus H3O plus. And so for here, we now have to set up an ice table. This is going to be just like the problems we were doing back in chapter 16, where we just had a weak acid. We don't have any other steps to have to worry about yet. So, when we do this, eventually I'm going to quit losing my pen. It looks different on my screen than yours, so I don't have the giant thing that helps me find it. Okay, so HF, the concentration we know from part A was 0.135 molar. Remember, it's ice table, so we can leave in molar. We don't have to convert to moles yet. We haven't added any base yet. Since there's no base added, we can stay with ice tables. So no water. We don't worry about water. We don't have any F minus at the beginning, and we have approximately no hydronium. Our change is we're going to be losing hydrofluoric acid since we can't be losing F minus because there's none of it. So that means we have to gain the fluoride ion, and we're going to gain some H3O plus. Our equilibrium condition then is going to be 0.135 minus X, but we're going to assume that should be a U, not a W. X is small, which means we're going to treat it like that part's not there. Water we're not worried about, and these are both X. So then we have that Ka is equal to F minus times H3O plus all over HF. So we'll plug our values in. Our Ka, and this time it was told in our problem. Sometimes in the exam you might have to look this up on the back of your exam. You'll have a big table of these. So Ka was 3.5 times 10 to the minus 4. That should be a 4. It should not be a 9. I'm trying my best. I don't have an eraser that's easy to use. And then we get F minus and H2O plus from our ice table. That gives us X squared. And since we assumed X was small, we get 0.135 here. And so we multiply these out then. And then we get that 4.73 times 10 to the minus 5 is equal to X squared. We can then take the square root of both sides. And we'll get that 6.87 times 10 to the minus 3 is equal to X. And in this case, remember that H3O plus is the same thing as X, so our H3O plus concentration is just this number. So then we can do the pH equals the negative log of 6.87 times 10 to the minus 3. And so we're going to pH equal to 2.16. And this is still in the acidic region, as we haven't added any base yet. So it would make sense that we would get something that's below 7. We have an acid. So that'll get us through part B. So now we need to go to what's going to happen once we add some base. And how is this going to look a little different than our other problem? So let's look at C. So we've now added 5 milliliters of base. And remember, once we've added something, now we've got to do a BAA table. So we're going to go with HF aqueous plus hydroxide aqueous is going to be an equilibrium, is going to go towards F minus aqueous plus H2O liquid. Note that I'm not as worried about the arrow, but the reason I'm doing this one directional arrow is we're not going to go back and reform our strong base. So there's still an equilibrium between the HF and the H minus, but it's not going to involve us going back here. We're just going to be forming towards this with this equation. So our before, if we calculate out, we get that we started with 0.35 times 10 to the minus 3 moles of this, no hydroxide, no F minus, and we're not worried about the water. Then our addition is we added some hydroxide. We specifically added 5.0 times 10 to the minus 4 moles. And then after the addition, the OH minus is smaller than the HF, so we're going to use up all the hydroxide. And the remaining, we're going to have 8.5 times 10 to the minus 4 HF. And then for our F minus, we're going to have 5.0 times 10 to the minus 4, because for every hydroxide you used up, you made an F minus. So now we need to know the two concentrations of our HF and our F minus. That way we can use the Henderson-Hasselbalch equation to find our concentration of the buffer we've created. Remember with your weak acid titration that when you're before the equivalence point, you're creating a buffer. That's why we're able to use the Henderson-Hasselbalch equation to help us out. So the new volume is 10 milliliters plus 5, so we have 0.0150 liters. We divide these, we get a concentration of 5.67 times 10 to the minus 2 molar. Now we're going to do the same thing with F minus. We've got 5.0 times 10 to the minus 4 moles over 0.0150 liters is equal to 3.33 times 10 to the minus 2 molar. So now we have pH equals pKa plus the log of the base over the acid. And that's going to be equal to 3.46 plus the log of base, remember that's our F minus, so 3.33 times 10 to the minus 2 over 5.67 times 10 to the minus 2. We plug all that in, and we get a pH of 3.23. So that'll get us through of what we've done when we've added 5 milliliters of base. We haven't yet reached the equivalence point yet, which is at 13.5 milliliters, so we're still going to be fairly acidic. And now, though, we want to see what's going to happen at the actual equivalence point. So let's look at that next. So once we get to D, what is the pH of the equivalence point? We need to note that for this, all of the HF has turned into F minus. That means that F minus, we have 1.35 times 10 to the minus 3 moles. Because every mole of HF has turned into F minus at the equivalence point, that's what it means to be there. Also, we have a new volume, so we want to find the concentration there. We don't have the original 10 milliliters. Now we have 23.5 milliliters. That's the 13.5 at equivalence plus the 10 we started with. And so that's going to give us a concentration of F minus equal to 5.74 times 10 to the minus 2 molar. So for this problem, we now have a weak base, and we don't have anything else there, so we've got to see how much the weak base turns back into the acid. So we've got to set up a titration, and this is just a weak base problem now, like we did back in chapter 16. So we have the fluoride ion plus water liquid is going to be in equilibrium with HF aqueous plus OH minus. So for this, we now have our ice table. Our initial here is 5.74 times 10 to the minus 2. We don't worry about the liquid water. We've used up all the HF, so we're now at 0, and this is approximately 0. Our change, we're going to lose some of the F minus because it's going to turn back into H plus. And so if we go to our equilibrium, we have 5.74 times 10 to the minus 2 minus x. And then we have plus x and plus x. Note that now we have the Kb equation, so we need to make sure we actually have the Kb. So I'm going to solve this up top here. Remember that Kb for our conjugate base is going to be equal to Kw over the Ka of the original acid. So that's going to be 1.0 times 10 to the minus 14 over Ka, which is 3.5 times 10 to the minus 4. And for that, we get a Kb equal to 2.86 times 10 to the minus 11. So Kp is really small. So even though the starting concentration isn't huge, it's still enough that we can assume X is small. So that means we're going to treat it like this part goes away to 0. So we can now set up our equation. So our Kb is equal to HF times OH minus all over F minus. And so we plug these in, we'll get X squared over 5.74 times 10 to the minus 2 is equal to the value for Kb. The value for Kp is 2.86 times 10 to the minus 11. So then we get X squared is equal to 1.64 times 10 to the minus 12. That came from multiplying both sides by 5.74 times 10 to the minus 2 we're going to square root both sides, and we're going to get that x is equal to 1.28 times 10 to the minus 6. So now I'm going to use that value to finish up the last bit of this, so I'm going to have to clear this slide. So now, to finish up D, we know that our OH minus, from what we just did, is 1.28 times 10 to the minus 6 molar. So for there, we can know that the POH is equal to the negative log of that number. So 1.28 times 10 to the minus 6. We get the POH is equal to 5.89. And then we want the pH, so that's just 14 minus 5.89. And that's going to be equal to 8.11 is our pH. We know that we should have a slightly basic system of the equivalent point for a weak acid. So that'll get us through D. So now we've got to look at one more part. What are we going to do when we have excess base? So we've got more base than we need to neutralize the hydrofluoric acid. So let's look at that. So for part E, we again are reacting HF aqueous plus OH minus aqueous goes to F minus aqueous plus water. So now we've got so let's see. So we have our BAA. So we started again with 1.35 times 10 to the minus 3 moles. We start with 0 hydroxide, 0 F minus. We don't worry about water. We then have our addition. We add no HF, but we add 1.50 times 10 to the minus 3 moles of hydroxide, no F minus, water. And then after our addition, we had more hydroxide than we had HF, so we're going to use up all the HF. And then if we subtract the HF from the OH minus, we'll find that we have remaining 1.5 times 10 to the minus 4 moles of hydroxide. And we have 1.35 times 10 to the minus 3 moles of F minus. Now in this case, since we have excess strong base, that's going to be significantly more important than than the F minus that we have left over. The OH minus is going to more significantly contribute to the overall pH, so we're going to just worry about the OH minus concentration, not the F minus. So we know that OH minus is equal to 1.5 times 10 to the minus 4 moles divided by the new volume, which is 0.0250 liters, and we're going to get that it is a 6.00 times 10 to the minus 3 molar solution of hydroxide. We can then find the POH is equal to the negative log of 6.00 times 10 to the minus 3 molar. We'll get the POH is 2.22, and then at pH is equal to 14 minus 2.22, which will give us a pH of 11.78. Is what we get in our problem. You'll notice that with this problem especially, that this is a fairly lengthy question, but it is systematically done the same way. So it's very important that you get comfortable with all of the different patterns so that you can do these more quickly. So because if you're spending a lot of time at each of these steps trying to figure out what to do next, these can take a rather long time. Also, it's important to note that you may have some questions that ask you to just do one step. Like maybe it's just what is the pH of the equivalence point, or what is the pH after 5 milliliters is added, or what after 15 milliliters, rather than asking all of this A through E. So you make sure you can do all of these, but be okay with only doing a couple, and don't rely on the fact that, oh, I had to do these in this exact order. Like if you're just asked E, you should be able to recognize you're after the equivalence point. Don't assume it's, oh, there'll be 5 questions, and the 5th one will always be after the equivalence point. So be able to identify conceptually each of these steps, how it fits into these different categories. So we're going to do one last problem. We're going to look at a Ksp problem. So we want to know if a precipitate's going to form if we take 255 milligrams of calcium sulfate and we add that to a 0.1 liter solution containing a 1.0 times 10 to the minus 5 molar concentration of lead 2+. So first we need to find out what the concentration of calcium sulfate is going to be in this 0.1 liter solution. So we've got our 255 milligrams, which is equal to 0.255 grams of calcium sulfate. And from there, we're going to use our molar mass, which is 136.14 grams, is equal to 1 mole, to say that there are 1.87 times 10 to the minus 3 moles of our calcium sulfate. We should also notice that calcium sulfate has exactly one SO4 2- for each calcium sulfate, so the number of moles of sulfate is going to be equal to the moles of calcium sulfate. Note that if there had been a coefficient like an SO4 and there were 2 of them, then you would have to double the number of moles before doing the concentration. So to find the concentration, we take 1.87 times 10 to the minus 3 moles. And we note that it is dissolved in 100 milliliters, so 0.100 liters. And we get that the concentration is going to be 1.87 times 10 to the minus 2. We then want to think about our Ksp, which is for PbSO4, which is going to be in equilibrium with Pb2 plus SO4 2 minus. So that means that our Q, remember we want to compare Q to K to see if we're going to have a precipitate, is going to be equal to the current Pb2 plus concentration times SO4 2 minus. Note that, remember, if you had coefficients in front of either the lead or the sulfate, they would act as exponents up here. They're just both raised to the 1 power because there's only one of each of those in this. So now we plug our values in. And we got our 1.0 times 10 to the minus 5 because the problem told us that was the starting lead concentration. And then we found that SO4 2 minus was going to be 1.087 times 10 to the minus 2. We plug those in. We get that Q is equal to 1.87 times 10 to the minus 7. We know that K, Sp, is equal to 1.82 times 10 to the minus 8. So Q is greater than K, and that means a solid will form. You have to in some way write this. You can't just say Q is greater than K. You can say it makes a solid won't form, however you want to put it. But somehow note that. So this is an example of how to work with Ksp for doing these problems.